Welcome back to the Math Professors. If you enjoy content that can be found in any college math class, please consider liking, subscribing, and sharing. I'm Professor Van Hamlin. I'm going to cover some initial value problems. Something that you'll see like at the end of a Calc 1, maybe even the beginning of a Calc 2 class. So, in this example, I've asked you to solve this differential equation, which says dy dx is equal to 3x squared plus 1, with this initial condition. So, basically what we're given is we're given this differential equation. And this is what we're trying to solve. When it says to solve an initial value problem, I'm trying to solve this equation. Now, with an algebra problem, you're trying to solve for a variable. But with a differential equation, you're trying to solve for the function. So I need the function that makes this true, to where if I take its derivative, I get this expression back. And also that function needs to have a solution point of 0, 3. So how do we go about that? In order to solve this, this differential equation, it's a differential equation because it's an equation that has a derivative in it. So the question really comes is like, how do you undo a derivative? Because my solution is a function. It's going to be some some y of x or some f of x if you prefer that label instead. I could say this is df dx if you prefer. And this is going to equal something. This is kind of our solution. Once I figure out what this y value is or what this function is, then I'm done. But again, it has to be true that when I take this thing's derivative, I get this thing. And also, this function goes to that point 0, 3. All right, so kind of back to the discussion. How do you undo this derivative? Well, what we're going to do is I know that the integral of dy dx, with respect to its variable, dx, is going to be, our function. It's going to be equal to this y function. So what I have to do, I have to integrate this thing in order to undo that derivative. So the integral of that 3x squared plus 1 with respect to x, remember that this dy dx is, this, thing up here. So that's what I've done. I've just, replaced it with that. And I know that, this is going to give us this function y. All right, so integrate this. The antiderivative of 3x squared is going to be 3x cubed divided by 3. So I know that this is going to be equal to x cubed, and I can check that. The derivative of x cubed is 3x squared. I'm happy with that. And then also I need to know the antiderivative of 1. Well, the antiderivative of 1 is just going to be an x. Now, things that we have to be careful with antiderivatives or general antiderivatives is we're going to have this plus c on here where c represents a constant because I know the derivative of a constant is equal to 0. So let's pretend like this c says 5. So the derivative of x cubed is 3x squared, derivative of x would just be 1, and the derivative of 5 would be equal to 0. So you can see like there's a 0 at the end of this. So there's always this plus c. And that's really why we have this piece here. So far I know this derivative is equal to, that 3x squared plus 1, but I have to guarantee that this solution equation goes to the point 0, 3. So we plug in x equals 0 and make sure that the y value is equal to 3. So now I'm going to plug this in here and find the c value that'll make this true. So when I plug in x equals 0, this would be 0 cubed plus 0 plus c is going to be equal to that wanted y value, which is equal to 3. Which, of course, you can solve these zeros will annihilate, so c is equal to 3. So finally, therefore, our solution to this equation is y is equal to, this x cubed plus x plus c, where c is 3. So this is going to be equal to x cubed plus x plus 3. Let's do one more first order, which means I just have a single, just a derivative in there, as opposed to like maybe a second derivative, and so on. So let's do one more of these. And then what I'm going to do is I'm going to use trig functions just to stay away from polynomials, and then we'll do maybe So our second example is solving dy dx, which is equal to the secant squared of x. So I want to find the y function that its derivative gives the secant squared. I need to make sure that goes to the point pi over 4, comma negative 5. So again, in order to find our y value, y is going to be equal to the antiderivative of this function, so secant squared of x, dx. And I know, what did I take the derivative to get secant squared? Well, it's going to be our tangent function, tangent of x. So again, the derivative of the tangent is our secant squared, so I know I did the antiderivative right, plus my, my constant. So far, its derivative is this thing. Now I need to make sure it goes through this point. So when I plug in pi over 4, y better be negative 5. So y will be negative 5 when x is equal to pi over 4 plus c. Now we know the tangent of pi over 4 is equal to 1. So negative 5 is equal to 1 plus c. So sending the 1 to the other side, negative 6 is equal to c. So therefore, our solution here is y is equal to the tangent of x minus 6. One more, that'll be it. That'll do a second order. So the next one we're doing is, I'm giving you a second derivative is equal to this function. So what we're going to see is we're just going to have to iterate this method twice. That if I'm given a second derivative, I know that its first derivative is going to be the antiderivative of the second derivative. With respect to x. And that, of course, is going to give us, this antiderivative of this 2 minus 4x dx. And then finding the antiderivative of 2 is going to be equal to 2x. So this is going to be 2x. Minus the antiderivative of this is going to be negative 4 times, our x squared over 2. And then finally plus our c. So I can simplify this to say that, dy dx is equal to 2x minus 2x squared plus c. All right. Now dy dx is the same thing as saying, y prime, right? So what I get to do is I'm going to use this initial condition because this is that first derivative, plug that in here. So when I plug in x equals 0, this y prime better be equal to negative 6. So negative 6 is equal to 2 times 0 minus 2 times 0 squared plus c. Again, all those will annihilate. So then, c is equal to negative 6. All right, so now I know that dy dx is equal to, this function here, so this expression 2 minus 2x squared, now c is equal to negative 6, so minus 6. All right, now remember I'm trying to find the solution to a differential equation is the original function y. So again, in order to find that, we know that integral of this, the integral of our 2x minus 2x squared minus 6 dx is going to be equal to that solution equation of y. So now the integral of this is going to be x squared. The integral of this is going to be minus 2. We're going to have an x cubed over 3. And then the integral of negative 6 is going to be minus 6x. And then we have plus a c. Again, how do we find that c value? Well, this is the function y, so I have to use that solution point for y, plugging it into this equation so we can see that y will be 2 when x is equal to 0. Again, x doesn't always have to be 0, that's why I did that previous example. Plus c. So again, all those first three terms of this right-hand expression in the equation will annihilate, so then c will be equal to 2. So finally, my solution is y is going to be, this equation with that correct c value. So this is going to be x squared minus 2x cubed over 3 minus 6x. C is 2 plus 2. And we are done. So if you like the content, please subscribe.